Greetings, everyone. Thank you for joining me once again. Before we start today's notes, I want to give you the justification for what we're about to do. So we've been solving quadratic equations, and so far we have two methods. We have solve by factoring and we have solve by square rooting. So suppose we had this equation. We could solve by square rooting because we would isolate the x squared and then we would square root both sides. So once we have something squared equals something else, we can square root both sides. Okay, so what we're going to do today is learn a method that helps us take any quadratic equation and change it into this form and square root both sides. And that process is called completing the square. So today we're on notes number 20, completing the square, or CTS for when you're texting. So what you're going to see here on this slide is I have three expressions on the left and three equations on the right, and you'll notice some similarities between the expressions and the equations. So we're going to kind of build this idea. I'm going to justify for you the process of completing the square. Okay, notice that for problem number 1, we have a perfect trinomial square. It factors into the same thing twice. It factors into x plus 5 times x plus 5, which we write as x plus 5 quantity squared. Number 2 is also a perfect trinomial square. So it also factors into the same thing twice, a minus 6 times a minus 6, and that would be a minus 6 quantity squared. And number 3, also a perfect square trinomial or perfect trinomial square. We could approach this one in a couple of different ways. We could factor out the 4, which is the best idea. Look for that greatest common factor and factor it out first. And then what we have left in the parentheses can be factored into m plus 1 times m plus 1, so m plus 1 quantity squared. Okay, now let's take a look at these equations, numbers 4, 5, and 6. So notice that we have the same perfect trinomial square in number 4 that we had in number 1, so we can rewrite this equation as x plus 5 quantity squared equals 17. And then it is of the form that I was talking about previously, something squared equals something, so we can square root both sides. So if we do that, we get x plus 5 equals plus or minus the square root of 17. And then to isolate x, we're going to subtract 5 from both sides. Now let's take a look at number 5. So again, we have the same perfect trinomial square that we had in problem number 2. So we know that's going to factor into a minus 6 quantity squared, and that equals 25. So now that we have something squared equals something else, we can square root both sides. The square root of 25 is 5. And we can add 6 to both sides. And we can also simplify this because we know that 6 plus 5 is 11, and 6 minus 5 is 1. And then finally, for number 6, we factor out that 4. We know that can be written as m plus 1 quantity squared. We can divide both sides by 4. And then square root both sides, and we get plus or minus 0, but plus or minus 0 is just still 0. So this one gives us m equals negative 1. So what we've seen in these three problems is that if you have a perfect square trinomial or perfect trinomial square, whatever you like to say, on the left side, then you can change it into a problem that can be solved by square rooting. But the question is, what if you don't? And what if you don't leads us to the process of completing the square. So let's say I want this to be a perfect trinomial square expression. So x squared plus 10x. Okay, x squared plus 10x plus what is a perfect trinomial square? And you can think of this as x squared plus 5x plus 5x plus what? And remember that that came from multiplying some factor by itself, so that would have to be x plus 5 times x plus 5. so that we would get 5x and 5x as the inside and outside. And so the lasts multiply to give us 25. So to make a perfect trinomial square, we need that number to be 25. So how does 25 relate to 10? If you look at what I did, 10 was divided into 5 and 5, and 5 is half of 10, and then we squared it to get 25. Now that's not the visual model yet. Here's the visual model. X squared plus 10x, or x squared plus 5x could be modeled like this. Let's say this length here is x, so this length here is x, and this other section here is 5, and that's 5. So x squared is the area of that square. 5x is the area of that rectangle. 5x is the area of this rectangle. So we have x squared, 5x, and 5x. Now, what do we need to make a complete square? You see how we have almost a square, however, it's incomplete. See, it's missing a chunk in the corner. What would it take to complete that square? Well, the way we get the area of each piece is by multiplying the length and the width. 5 times 5 is 25. 25 completes the square. It makes a perfectly completed square. That's why we use that phrase. Okay, so what we're going to do next is find the number that makes a perfect trinomial square in each of these expressions. So if you had x squared plus 16x, think of that as x squared plus 8x plus what? Think of that as x plus 8 times x plus 8 to get the 8x on the inside and outside. So what would that last number be? It would be 64. So 64 completes the square. So we've seen now twice that we need to take half of this number here and square it. So that's going to be our shortcut. Half of this number here in number 8, half of that number there would be -2, square it, and we get 4. So that would be a perfect trinomial square, and it would factor into x minus 2 times x minus 2. Now, what if you have an odd number there? Instead of an even number, you can still take half of it, but I would caution you not to use a decimal, use a fraction. Half of that number is 7 halves, so we're looking at x plus 7 halves times x plus 7 halves. 7 halves times itself is 49 fourths. It's a lot easier to work with squaring numbers and square rooting numbers if you're leaving them as fractions, and in particular improper fractions. So let's not do 3.5 here. So in general then, if you have x squared plus bx, the number that completes the square is going to be whatever you get when you take half of b and then square it. So b over 2 squared, or you can think of that as b squared over 4. And then similarly, if you're subtracting, then when you take half of negative b, you have negative b over 2, but when you square it, you get the same final result. You get a positive. So either way, you kind of don't have to pay that much attention to that sign there, because you're going to get b squared. Well, let me write it the same way. You're going to get b over 2 quantity squared. Okay. So now let's take a look at these examples. Let's solve each equation by completing the square. And that means figure out how to make this expression a perfect trinomial square if it isn't already. So x squared minus 10x plus 1 is not a perfect trinomial square. What I like to do if it's not a perfect trinomial square is I like to keep my x squared and my x terms, leave a space for the number I'm going to add to complete the square, subtract the 1 to get the constant over to the other side, and naturally, if you add a number to one side of an equation, you have to add the same number to the other side of the equation to keep it balanced. So we have to add to the left and the right. Okay, what completes the square? Take half of -10, which would be -5, and square it, and we get 25. So we add 25 to the left, and we add 25 to the right. So now we can factor that into x minus 5 quantity squared, and on the right side we have 24. Now we're ready to use square rooting because we have something squared equals something else. So square root both sides. X minus 5 equals plus or minus the square root of 24. Add 5 to both sides to get x by itself, and simplify the radical if you can. So this is going to be 2 square root 6. So our answers are 5 plus 2 square root 6 and 5 minus 2 square root 6. Leave your answers as exact answers, no need to change them to decimals. Let's do number 12. X squared plus x plus 16 is not a perfect trinomial square. So what I'm going to do is leave the x squared and the x terms, leave a space for the number that completes the square, subtract 16 from both sides, and remember to add to the right whatever I add to the left. So the coefficient here on the x term is 1. So we take half of that number, that would be 1/2, and we square it. So 1/2 squared is 1/4. So 1/4 is the number that completes the square. That's what we add to both sides. And that means this is going to factor into x plus 1/2 quantity squared. And on the right side, let's think of negative 12 as negative 48 fourths, and we'll add 1/4 and we get negative 47 fourths. Once again, if you work with fractions, and in particular improper fractions, it's going to make the next step much easier. Okay, so we're going to square root both sides. So we have x plus 1/2 equals plus or minus the square root of negative 47 over the square root of 4. You can break it up when you have the square root of a fraction and do the square root of the top and the bottom separately. Now to get x by itself, we need to subtract 1/2 from both sides, and we also need to simplify our radical. So because we have the square root of a negative, we know that to be an imaginary number, so we're going to call it I square root 47, and then on the bottom, square root of 4 is 2. So our answers are negative 1/2 plus and minus I square root 47 over 2. Okay, now we move into the higher complexity problems, such as number 13. You might have noticed in all the previous problems we did that the coefficient, the leading coefficient was 1. 1x squared, 1x squared, 1x squared on all of these. Well, what if the leading coefficient is not 1? Like in this case, what if it's 3? We need to change the equation so that the leading coefficient is 1 in order to complete the square. So in this case, divide both sides of the equation by 3. So that gives us x squared minus 12x plus 50 equals 0. Even if the numbers are not all divisible by 3, you have to do it anyway, and you'll just have fractions. Okay, so now to complete the square, we don't have a perfect trinomial square yet, so I'm going to put a box to represent what I'm going to add to complete the square. I'm going to subtract 50 from both sides, and then the box on the other side. So now we take half of negative 12, that would be negative 6, and we square it, and that's 36. So 36 is the number that completes the square, allowing us to factor this into x minus 6 quantity squared, and then adding the numbers on the other side, we get negative 14. So now we're ready to square root both sides, and then simplify. So let's add 6 to both sides, and we get x equals 6, plus or minus, and let's change the form to I square root 14. Okay, just a couple more things to do. Here's a word problem and a geometry problem, 2 for the price of 1. The area of the triangle is 144 square inches. What is the value of x? Okay, so we know the formula for the area of a triangle, right? What is it? That's right, 1/2 times the base times the height. And the base and the height have to be perpendicular. So we have x plus 10 for the base, and we have 2x for the height. So the area, which is 144, is equal to 1/2 times x plus 10 times 2x. Now let's go ahead and simplify, because we can multiply the 1/2 and the 2. And now we have 144 equals x times x plus 10. So this is a quadratic equation. We can distribute the x, and we have 144 equals x squared plus 10x. Okay, now let's complete the square. So I'm going to go ahead and figure out what number to add to both sides so that on the right side there will be a perfect square trinomial, or a perfect trinomial square. So let's take half of 10, which is 5, and square it, 25. So let's add 25 to both sides. And that gives us 169 equals, let's factor the right, x plus 5 quantity squared. Now we're going to square root both sides, and we get plus or minus the square root of 169 equals x plus 5. And 169 is a perfect square. Its square root is 13. So we have plus or minus 13 equals x plus 5. So now we're going to subtract 5 from both sides to get x by itself. And I kind of like having my x on the left side, so I'm just going to rearrange it like that. So when we subtract 5, we have negative 5 plus or minus 13. Negative 5 plus 13 is 8. Negative 5 minus 13 is negative 18. But remember, in the context of this problem, the height and the base should be positive numbers. So negative 18 is not going to make sense. So that one's extraneous. So just x equals 8. And to double check, that would make the height 16 and the length or the base 18. Half of 16 times 18 would be half of, or sorry, that should be a 2 for a half, right? Would be 8 times 18, and that is 144, so that checks. Okay, we have a little bit more. Yep, just this last one, these last couple of problems. Use completing the square to convert from standard form quadratic functions to vertex form. So this takes us all the way back to the beginning of the chapter. Remember when we learned standard form, which looks like this, and we learned vertex form and intercept form? So vertex form is really handy for graphing and being able to tell what your vertex is. And vertex form looks like this. Remember, y equals some number a times the quantity x minus h squared plus k, where the vertex is hk. So completing the square is going to help us convert from what we have into that form. So what I'm going to do is figure out what to add to x squared minus 8x to make a perfect trinomial square. And I'm going to do something a little bit different this time. Instead of adding numbers to both sides of the equation, whatever number I add to the right side of the equation, I'm also going to subtract from the right side of the equation, because adding and subtracting the same number is essentially just adding 0. So that's another way to keep the balance without changing the right side, or excuse me, the left side. And I don't want to change the left side because I just want to have a y over there, and that's what I already have. So the number that would complete the square would be 16. Half of negative 8 squared is 16. So we're going to add 16 and subtract 16. So now this part of the problem is the perfect trinomial square, and it factors into x minus 4 quantity squared. And this part of the problem we can add together and get 1. So there's our vertex form. And you can see from that that the vertex is a 0.41. Okay, let's do this last one. Notice that the coefficient is 3, so we're going to have to employ that idea of, well, what we did in the previous problem was we divided by 3, but I don't want to divide both sides of this equation by 3 because I want y to just be y. So instead of that, what we can do is factor out the 3. So the 3 is still there, it's factored out. So we have y equals 3 times the quantity x squared plus 7/3 x. And then we're going to add some number to complete the square. We don't need to factor the 3 out of the minus 2, but we are going to have to add to the end whatever is necessary. Okay, so what number is going to complete the square? So here we have 7/3. Half of that is 7/6, and when we square 7/6, we get 49/36. So I just added 49/36. Does that mean I also need to subtract 49/36 out here? Well, not exactly, because I actually added 3 times 49/36. So I need to subtract 3 times 49/36, and that means I'm subtracting 49/12. So you have to think that through and make sure that you keep the equation balanced. So now that we have that, we have y equals 3 times the quantity x plus 7/6 squared. And then when we combine the minus 2 and the minus 49/12, let's see, negative 24 and negative 49 would be negative 73, I think. So negative 73/12. So there's our vertex form. And from that, we could see that the vertex is a point negative 7/6, comma, negative 73/12. And we also would know, if we were graphing this, that there would be a vertical stretch by a factor of 3. Okay, so that's completing the square. That was section 4.7, and here is your homework. Thanks, everybody.